What if you could predict the future with just a simple shape? Well, today we're going to dive into the bell curve, a really powerful statistical tool that helps businesses take all that messy uncertainty and turn it into confident million-dollar decisions. All right, put yourself in this spot. You're a manager at the Greer Tire Company. Your team just created a fantastic new tire. But now comes the million-dollar question. What do you set the mileage guarantee at? If you go too high, you could lose a fortune on replacements. But if you go too low, nobody's going to trust your product. This isn't just a guess, it's a high-stakes calculation. And lucky for us, the data holds the answer. So the tool that's going to help us out here is one of the most powerful and, honestly, most common patterns in all of statistics, the normal distribution. You probably know it as the bell curve. It's this predictable shape that just shows up almost everywhere. And when I say everywhere, I mean literally everywhere. From the heights of everyone in a country to your exam scores, to how much rain falls in a year, even down to tiny scientific measurements. This bell shape is a fundamental pattern of our world. If you can understand it, you can start to understand and predict outcomes in a ton of different fields. Okay, so what's the big deal with this shape? Well, it's a perfectly symmetrical curve. And what it shows us is that most results, whether it's tire mileage or test scores, are going to cluster right around the average. And the further you get from that average in either direction, the fewer results you're going to find. It's this super simple idea that makes it so incredibly powerful for making predictions. Now, you only need to know two things to understand any bell curve. The first is the mean, or the average. Statisticians use the Greek letter mu for this. This just tells us where the center of the bell is. A higher average shifts the whole curve to the right, a lower one shifts it to the left. Think of it like the curve's location on a map, its home base. And the second thing is the standard deviation, which we call sigma. This decides the actual shape of the curve, how spread out or squished together the data is. A really small standard deviation means all the results are packed tightly around the average, so you get a tall, skinny curve. A big one means the data's all over the place, giving you a short, wide curve. Okay, but wait. How do you compare, say, tire mileage in miles with something totally different like test scores in percentages? It's like comparing apples and oranges, right? Well, we need a common language, a translator, and that's where the z-score comes in. It lets us translate any bell curve into one single universal blueprint. And this is that master blueprint. It's called the standard normal distribution. It's a very special bell curve that's always centered at 0 and always has a standard deviation of 1. By converting our own data to fit this blueprint, we can easily figure out probabilities for pretty much any situation. Okay, let's bring this back to our tire problem. So Greer knows from years of data that their tires last on average about 36,500 miles, give or take 5,000 miles. That's their standard deviation. The big question is, what's the probability a tire will last more than 40,000 miles? We can solve this in two simple steps. First, convert that 40,000 miles into a universal z-score, and then we'll find the probability that's linked to that score. So you run the numbers through the formula, and bam, you get a z-score of 0.7. Now, this single number is super powerful. It tells us that a tire lasting 40,000 miles is exactly 0.7 standard deviations above the average. We've just taken a specific real-world number and placed it perfectly on our universal map. Now, we're all set to find the probability. And that z-score, that 0.7, it points to a very specific area under our universal curve. You can look it up in a table or just pop it into a spreadsheet, and you find out that area is 24.2%. So what does that mean? It means there's a 24.2% chance any given tire will last longer than 40,000 miles. And just like that, Greer isn't guessing anymore. They've got a hard number to build their whole warranty strategy around. But hold on a second. That seems almost too easy, right? And, well, it kind of is. We just made a huge assumption. We assumed we knew the exact average and standard deviation for every single tire Greer will ever make. But in the real world, you almost never know that. So what happens when you're working with incomplete information? What if you don't have all that historical data? What if you're a startup and you've only done a small test on, say, 28 tires? The true average and spread for all the tires you'll ever make is a complete unknown. And that uncertainty, it changes the whole game. So, for this messy, more realistic world, we gotta pull a different tool out of our toolkit. And that is the t-distribution, and its sidekick, the t-score. This whole system is designed specifically for the uncertainty that comes with working with smaller samples when you just don't know the full picture. You know, the difference is actually pretty clear. The normal distribution with the z-square, that's for the ideal world, where we know everything about our population. The t-distribution, on the other hand, is for the real world, where we're working with estimates from a smaller sample. The shape of the t-curve even changes depending on our sample size. The smaller our sample, the more cautious the curve becomes. And you can actually see the difference right here. The t-distribution has what we call heavier tails. See how they're thicker at the ends? That's not just for looks. It's basically the math being more cautious. It's building in a safety net. It acknowledges that with a small sample, you have way more uncertainty, so it cautiously gives a little more weight to extreme outcomes. It's statistics being realistic. All right, so let's go back to Greer's tires one more time. But now, let's be realistic. We only tested a sample of 28 tires. We used the more appropriate t-distribution instead, and our answer changes slightly. The probability of a tire lasting over 40,000 miles is now 25.0%. Now, it might not seem like a huge jump, but it's a more honest, more accurate number because it accounts for what we don't know. So look at what we've done here. We've gone from a theoretical problem to a really practical, data-driven decision. We now have two incredibly powerful tools that can handle both those ideal, perfect information scenarios and the messy reality of having limited data. So how do you know which one to use? It's actually really simple. Here's the cheat sheet. If you know the standard deviation for the entire population, which is pretty rare by the way, then the z-distribution is your go-to. But if you're like most of us, working with an unknown population and a smaller sample size, the t-distribution is the safer, more accurate choice. It's really the right tool for real-world data. And this really sums it all up. The t-distribution is basically a reality check. It's the statistical way of saying, hey, we're working with a sample, not the whole shebang, so let's build in a little extra buffer for that uncertainty. It gives us results we can actually trust more. So the next time you're facing a big decision and you're just staring at a bunch of uncertainty, think about the bell curve. Ask yourself, am I living in that perfect z-score world with all the data? Or am I in the real t-score world where I need to be a bit more cautious? Because thinking this way, well, it can help you make way smarter, more confident choices. So what's one decision in your world you could look at with this new mindset?